Okay, good afternoon, everybody. My name's Martin Jolly, and I'm currently studying my first year of my PhD. I'm researching image velocimetry, which is a technique that's been around for decades, but only now being adapted to deal with river flow challenges. I'm being funded by the EPSRC, and I'm working in partnership with the Environment Agency. It may not be a technique that many people are familiar with, so with that in mind, I wanted to take some time to explain the fundamentals of my PhD topic. And instead of simply telling you what it is I'm looking at and what I'm doing, I wanted to take a moment just to help you understand why I'm taking the route that I am. So IB is a tool, it's a method that can be the basis for loads of different studies and uses, of which we'll be discussing a little bit later in the presentation. I'll be looking at addressing what IV is and why we need it and how we can use it. So to better do that, I'll be breaking down the topic into three simple headlines. So I'll start by looking at the fundamentals of IV, then I'll be looking at the workings of my PhD, where the ideas stem from basically, and then I'll be explaining my plan and where I want to take my PhD and why I want to do that. So the fundamentals can help the understanding of how we best use that technique. So I'll be explaining quickly what IV is, where it came from. I'll show a 5-minute animation of how it works, and then I'll start to discuss why we need IV. So put simply, IV has a process that allows us to capture sequential images of flow and track visible traces on the surface to begin mapping either velocity in terms of areas or as vectors of individual particles. A little bit more on that later when I show you the animation. The beauty of IV is that it requires very little specialist hardware. It makes it a really cost-effective method of velocimetry compared to other methods such as ADCPs. On top of that, IV is non-intrusive, so it increases the safety of operatives and minimizes the risk to the equipment. This is something that can be really appealing to the practitioners who have to go off the site sometimes on their own or work at high-risk areas with fast and deep flows. So the prints of IV date back hundreds of years to Leonardo da Vinci, who would disperse traces along a river and then draw the interaction they would have with the flow. Fast forward a few centuries when cameras were established, Ludwig Prandtl started experimenting around aerodynamics and developed theories around fluid boundary layers, which is used in all aspects of aeronautical engineering and several other subjects. And then we come to modern methods. So modern IV began with the invention of lasers back in the 60s, which was used to light up particles in a flow in controlled lab settings. And then in the past 30 years, research really began to expand the area that IV can handle. And that's put a real emphasis on the large scale IV, which has been applied to river flows. So the way that modern methods typically work, they produce velocity calculations through either cross-correlation methods or sequential images, or through the tracking of individual particles between frames. So I'll discuss that a little bit further now with my highly detailed, highly intellectual, state-of-the-art animation.
Meet Jimmy and his best friend Jenny. They love cycling and they want to find out who has the highest top speed. They could buy an expensive piece of equipment and work it out that way, but Jimmy can't afford that. They could film some laps, says Jenny, and work it out that way. Fantastic idea, says Jimmy. But how? So initially, Jimmy has an idea. He splits a 400-meter racetrack out into 50-meter sections, and he says that if we time how long it takes for us to pass each of the checkpoints, we'll know our average velocity between each checkpoint. And that way, we can find out our max from there, as velocity equals distance over time. So they break down each section and worked out their quickest 50 meters. Jimmy's quickest worked out as 10 meters per second, and Jenny gets around 7. So Jimmy's times at each checkpoint are shown here in pink, and Jenny's are shown here in orange. These represent the velocity of each person at each specific point in space and time, shown here as a blue dot. Because we know where they started, and we know where they finished, and we know how long they took between the two, well, then we've worked out their velocities. So to conclude our findings, Jimmy's the winner. He went 10 meters per second, whereas Jenny could only manage 7. Clear? Well, perhaps not. Jenny has a better idea. She felt she was going fastest between 2 of Jimmy's checkpoints. So Jenny wants to track her own velocity the whole way around the track. This graph shows that she was actually fastest at around 160 meters, which is between two of Jimmy's checkpoints, which means 7 wasn't actually her top speed. By focusing on Jenny instead of as an individual means that we can more accurately track her velocity throughout time rather than at a fixed point in space. We can measure the distance that she travels, which we can physically see, and we know a fixed time difference between each position, which we can use frame rates for. This gives us dt, which is a small time difference, and dx, which is a small distance difference. And with that, we get dx over dt, which is velocity. So Jenny actually went faster than Jimmy. Unlucky Jimmy. But how does this all relate to my research? So here we have a river with some visible traces, which could be anything from naturally occurring foam to traces placed in the stream. Let's look at Jimmy's method, also known as Eulerian. Let's set up checkpoints like he did, and instead of bikers, let's look at a collection of particles in an area of interest. Let's say that we previously worked out its initial velocity at 2 meters per second as it hits checkpoint 1. The distance between checkpoint 1 and checkpoint 2 is also known as 10 meters. We know a distance, we've measured a time, and therefore we can calculate a velocity. But this is only in relation to those specific checkpoints and not in between. To measure the time, we can use things such as the frame rate. But what about Jenny's method, otherwise known as Lagrangian? Let's look at a specific particle instead of a collection of particles, and let's call it P1. P1 will have a known location in terms of coordinates, say here 2 and 1.7, at an initial time of t0. Now, at a later time of t1, it will have moved. At t1, its new coordinates are 4.9 and 2.4. The difference between the two times is t1 minus t0, and the difference in distance will be the length of the hypotenuse, worked out at 2.9 squared plus 0.7 squared, all square rooted, which comes to around d1 equal around 3 meters. So the velocities would be the distance over the time, making it 3 meters over 1 unit of time. What if we have loads of particles? Do we measure them all? What if instead of a particle, we tracked a group of particles at fixed points at distance intervals to measure the velocity? Well, that's Euler, also known as Jimmy's method. But how does this relate to my work? Well, Euler is the basis of PIV, which looks at the sequential images to calculate velocity. Whereas Lagrangian is PTV, looking at individual particles and tracking their movement in relation to time.
So now that we better understand the process that IB software undergoes to calculate the velocity, we can now see examples of how each of the software maps velocity as an output. On the left-hand side, we have PIV. You can clearly see the interrogation grids and how it sets itself up to map the velocities, with each grid feeding into the next, with a directional arrow and a color representing the velocity associated with that area. It's a really nice way, a simple method of mapping the velocities, as it's a clear visual of the flow. Alternatively, on the right-hand side, we have vectors representing the direction and the magnitude of velocity of the surface. So this is the PTV method where individual particles have been tracked along the flow. Both of these images have a first step and an arrow moving down to the second step. So this is the orthorectification stage of the process, where the raw image, which is image 1, is transformed to an image which has uniform distance associated with each pixel. So this removes things like distortion that the cameras and lenses have associated with them. So now that we understand a bit more about PIV and PTV, I need to answer why surface velocity and IV is so important. So as IV research expanded, its uses and its methodologies are rapidly evolving. Other methods of measuring velocity rely on contact with the water surface, which can be really problematic in high flows due to the energy and the state of the river. As well as that, many types of remote sensing gauges may only provide point-specific or sometimes at best cross-sectional. IV doesn't require contact with the flow, making high energy flows less of an issue. So that's regarding hardware and safety, but it can also provide a 2D map of the surface velocity, as we've previously seen, rather than just cross-sections or points. Then with that, we can use some good assumptions about the velocity below the water surface, dependent on the depth. So the non-intrusive aspect of IV is a major player. It means remote sensing can be accomplished in many different ways, but also means maintenance is a lot less likely to be needed, in remote sites when a high flow strikes. So remote sensing has the capability of reducing the amount of hours required for data collection, depending on the type of remote sensor used as well. So that nicely brings me on to my next point, which is that IV can either be a fixed location, constantly monitoring a specific area, or it can be carried out using UASs. So the UAS is a large focus point for quite a lot of research at the moment in the field. So a vast amount of data can be potentially captured in short amount of time with minimal physical efforts, which is something that could be real great use to practitioners who have to go out and collect river flow data on a regular basis. Now that we kind of have an understanding of how IV works and the principles behind the software, we need to better understand what it is we're looking at. So at the moment, there's a lot of emphasis on how the software works, coming up with algorithms and trying to develop it further within academia, which is really important because we need to understand the software's limitations and its strengths. But there's also the possibility of the software to be used in industry. So we also need to establish where the software can be adapted, where it can be used, and most importantly, where it can't be used. So when I say industry, my focus is primarily operatives such as the Environment Agency, who have to routinely go out and measure and maintain river data. But it can also apply to anybody who uses this technique as a tool to further their own work and research. So within academia, there's a lot of focus on the processes of the software. So we're looking at the development of the algorithms, its pre and its post processing, and the understanding of each of these, as well as environmental limitations. So this means exploring the accuracy of the software in varying conditions. And then within industry, wants and needs different things from the software. So one of the most important functions of IV is its ability to produce velocity output without needing contact with the water surface. So that's particularly vital for safety in high flow conditions for both equipment and operators. And then with that being said, these are kind of the three main points that I've highlighted to focus on regarding progressing IV into industrial practices. So for me, the most important aspect is the cost benefit analysis. Is it worth the time and money in its investment? Because if it isn't, then we need to start adapting IV more to make it more worthwhile, because working with industry could potentially accelerate the research as it presents new possibilities for them, but also there's a possible increase in funding along with that. So with that simple overlook into what IV can do for us and where we can possibly take it, I came up with this research aim for the time being, and it's to provide a clear, comprehensive study of the limitations and challenges that modern IV faces for river flow data acquisition. Although there's that real focus on the application to industrial practices, it still needs to focus on progressing the software and really working on mitigating its error boundaries so that the software becomes more malleable later on when applying it fully into practice. And then to summarize all of that, we start to formulate this plan, looking at the fundamentals and the workings of IV. We start to build this focus as advancing the research more to an industrial-led process. We're starting to look at the importance of feeding into the applications of IV and how it's actually going to be used on a day-to-day basis. And then with that in mind, I produced the 4 crucial steps, or the 4 papers or chapters in this journey of IV application to industry. So I start with a paper that collects all of the information that's currently out there regarding algorithms behind the software and the building blocks or the foundations of which they're built. And then I use that first paper to highlight the areas of weakness that haven't been fully explored yet. So I work on highlighting further issues and limitations to practice and how they can be resolved. And then with that study in mind, I'm able to then start idealizing techniques to more efficient ways in practice. There's a massive focus on using drones to produce velocity maps of rivers. And then finally, I'm going to look at how all of that sits in industry. How can it be used to build and validate river flow models in varying states and conditions? And I know that those 4 focuses may not be enough to start rolling out the technology worldwide, but it does begin the process of building a steady rapport for the use of IV in industry. So my methodology for the papers looks a little something like this. The 4th paper, it's really hard to write a methodology for it because it uses the previous 3 papers. So I came up with the methodology for the first 3 here. So after reviewing the literature in the first paper and highlighting the known unknowns, I'll start to be able to experiment with the software, critique each process stage of the software from pre through to post processing. And then I'll be able to come up with impact factors on the effect that error has on accuracy to better understand what's most important to the technique. So for example, what processing values produce the largest error boundaries and variations on velocity output? And then how can we adapt the software to help the user understand what the boundaries are so that it's easier for them to better calibrate the model for increased reliability? The techniques around the processing of the software isn't the only variable involved though. There's also external variables such as environmental characteristics seen by the image capture. So that means testing the effects that environmental settings have on the accuracy of the output. So such things as wind speed, wind direction, state of flow, glare, you've got rainfall patterns on the surface, ponding in the river, and so on. That will lead to even more error boundaries, but what pre-processing can we do to minimize those effects? So are there correction factors that we can apply to the processing if we know the variables such as the wind speed and the wind direction? Then we have all of that to apply to drone usage too. So with the added challenges of stabilization and advances in how we use drones to capture more and more usable data for us. But there's also this, how can this research be developed in the future to start implementing the method into a more practitioner-friendly manner? So just to touch on drones a little bit more, this is a processed video image captured from a drone over a slowly flowing river with traces manually placed in. The video on the left shows a pre-processed video which has been rectified in grayscale to better show the white traces, which looks like tiny white specks on the image if you look really closely. Also visible are some of the GCPs which are used to auto-rectify the images, converting pixels into dimensional areas. Top right, we have the location of the drone mapped in 3D as to better understand the process that the programs undergo when producing stabilized images. So a shift in the X and Y coordinates will affect the velocity values as it alters the seeding displacement, while a change in the Z coordinate will affect the pixel size. So then moving on to the bottom right, we have the video that's been processed and the vectors mapped onto the stream for a visual representation of the flow. So that's an output that we get then from the software that we've used. So this is all kind of the building block of what can be really promising applications of UAS in the field. So challenges that are to be overcome are still presenting themselves, but currently we want to know, how can UAS IV be used more efficiently? So do we need GCPs? What tracer density do we need for reliable, accurate results? What's the minimal stabilization required to produce good results? And then that brings us on to the conclusion. So to conclude, IV is still at its early stages of development with loads of different routes for research that can be taken. Questions really need answering regarding the limitations of the software so that processes can begin to mitigate the error that's related to them, while the methodologies of both fixed and UAS systems need idealizing. So a key focus of mine is to look at the challenges that IV will face when looking to take the software from academia into a more industrial practice, and how the software can best overcome that. So to do that, we need to fully understand the strengths and the weaknesses of the methods, and then produce a way of the user to better understand and self-mitigate error bounds related to the velocity outputs. So that's regarding input variables and external variables such as the environmental factors. So that was broken down into a 4-phase thesis with papers produced for each. The first one being the lit review for the current research and the known problems. And then the second paper is the experimental review stemming from the findings and the known unknowns of the problems. And then the third paper is the idealization of all of the limitations and errors related to variables towards use in UAS IV. And then finally, how can we do that in more of a towards validating hydrological models in flood management processes, but in an efficient manner. So all of that feeds into what we want to find out relating to my own aim of pushing IV into a more industrial practice method. And that involves finding the limiting factors of IV, so finding out how to mitigate the errors associated with the variables that are both controlled and not controlled, such as the environmental impact. And then finally, how can all of this be used when looking to produce usable models from the data collected and the processing using IV? So that's everything I've got. Thank you for your time this afternoon.